Welcome, everybody. So today is my great pleasure to invite our guest, Eva Pastorczak, to give a presentation entitled Insight from Numbers, How Quantum Chemistry Exploits Physics, Mathematics, and Computer Science to Understand Nature. Welcome.
Thanks. I was told that you know a little bit about Schrödinger's equation, so I'm already quite happy. It will be a bit easier. So just let me tell you that I'm part of this group in quantum chemistry group in this Institute of Physics. This is my boss, Katarzyna Perna, and these are some people. The group changes all the time because we have students, PhD students, and postdocs. So it's not a constant. These are not constant ingredients. So we are going to talk first a bit about what is quantum chemistry, and then about our research, just a piece of our research. So one of the people who were like great grandfathers of quantum chemistry was Charles Paulson, and he was a mathematician, and then he became a chemist, and in between he did some work. He wrote some books on religion, so he was really, he had broad interests, and there is this quote that is very popular by him, give us insight, not numbers. So chemistry, like, what would you say chemistry is as a science? It's a science that describes something, right? If you just go back to your high school or middle primary school, then chemistry was about what?
So reactions.
Reactions, right? Molecules, right? So chemistry was like that in the 19th century and before. People were like pouring liquids and observing like little explosions and stuff like that. And then, of course, like every science, they wanted it to be a bit more ordered, and they wanted to see some theory behind it. So theoretical chemistry was born, but it was very kind of in terms of, everything was kind of in terms of pictures, so like bonds, interactions between atoms, between molecules, and there was some math behind it because you had to, pour 2/3 of some substance and 1/3 of some substance to create a reaction. But it was really like very far from what we see today as exact sciences. But then it changed, and it changed with your old friend Schrödinger's equation. Right, so Schrödinger's equation is this innocent-looking formula, and of course the reason why it's both innocent-looking and horrible to solve is that the wave function, is a multi-dimensional object, and this is not a number or a function, but an operator, right? So you don't have multiplication here. You only have multiplication here, so we have energy times wave function is equal to the Hamiltonian acting on the wave function. And this was the kind of, around that time, this was the first time people realized that energy. So energy has levels, right? So if you have an atom or a molecule, it cannot take any energetical state, but those discrete states, right, that have gaps between. Okay, so this was how quantum physics was born. So when do you think quantum chemistry was born? Like, give me a number.
Perhaps 20 years after.
20? Do we have more? Do we have less in here?
5 years later.
5? Okay, so this is considered the beginning of quantum chemistry, when those two guys were able to describe the hydrogen molecule. So that was 1927, right? 2 years later. Just they took the Schrödinger's equation and they applied something called Born-Oppenheimer approximation. That is, we'll talk about later. And took some symmetry into account. And they showed that this is they calculated the dissociation curve of the hydrogen molecule. And as years go by, people call quantum chemistry a useless science, but quantum chemists don't give up. And in 1998, the first Nobel Prize for quantum chemistry was given to Walter Kohn and John Pope. This was basically, well, for a few different things, but basically for expressing this problem, so the problem of calculating the energy of a big quantum system, from a many-body problem to a problem of density function. So this was very important because like if you have story online people, if there are any, you can Google it. So if you have the wave function, then this is a function of all the coordinates of all the particles inside the system, right? So we have the first electron, so we have x1, y1, z1, and spin on top of it, and so on, right? And then we have x and y and z and this is 4 times n dimensions, right? But Walter Kohn expressed this problem of energy calculation as a problem of finding the electronic density, which is the function of only 3 coordinates. Right, so it simplified this problem very considerably. At the same time, it didn't solve it completely because of the fact that we know that energy is a function of electronic density, but we don't know the formula, so we have to guess. And finally, well, not finally, I hope alive and I'm a quantum chemist, but not so long ago there was the second Nobel Prize in quantum chemistry. It was given to Arie Borscha, and this was given for developing methods that were able to model very chemical reactions with huge molecules, because these are enzymatic reactions. So generally reactions that happen in human or animal bodies, and those molecules are huge. So from this kind of useless science that can only be applied to small molecules like hydrogen or water, we moved on to enzymatic reaction. And this is the problem, right? That we have the Schrödinger's equation, and kind of if we knew how to solve it exactly and let's say efficiently, we would be able to describe all kinds of things. Well, of course, chemical reactions, but also light matter interactions. So how when you shine some light on a system, what happens? Sometimes a reaction happens, sometimes something else happens, and so on. Also, molecular interactions. So how molecules interact with each other without going into a chemical reactions. Those are very important for well, for many things, but basically for how different materials are built. And of course, for molecular and supermolecular structure, we could calculate the geometries of molecules, structure, crystalline structures. But the problem, as I said, is, well, the wave function is a huge object, hugely dimensional, and the Hamiltonian is an operator that depends on, if you look at a molecule, right, the molecule has nuclei, and it has, I have a laser pointer, those nuclei, right, and it has electrons that are around the nuclei like a cloud. So we have an operator that contains the electronic part. So this is kinetic energy of the electrons, kinetic energy of nuclei. Then there is the interaction between nuclei and electrons, electron-electron interaction, and nucleus-nucleus interaction. And so again, complicated object. So now we go to this very early achievement of quantum chemistry that is fundamental, and we are still using it. And if we stopped, basically the whole quantum chemistry would be dead. The Born-Oppenheimer approximation. So we know that nuclei are very slow and they are very heavy compared to the electrons. So we can say the electrons, the electronic movement can be separated from the movement of the nuclei. And we can separate both the Hamiltonian, electronic Hamiltonian, and the wave function. So we could just solve the problem for the electron part of this wave function. So then we only have this part of the Hamiltonian, which is much simpler, right? And we basically got rid of about half of the problem, right? But still, if you only had this problem to solve and like took a water molecule like here and thank you. you wanted to solve this equation for the water molecule just with like a pencil and a piece of paper, you would just sit and cry because it's not possible, right? So you need some kind of further approximation and some kind of help, right? Help in the form of a code, a computer, and but what then? What can you look? So instead of thinking like how to solve the Schrodinger's equation, we can ask ourselves what we're interested in, right? So, well, first of all, we're interested in the energy, the ground state energy, so the lowest possible, and then the higher ones. So, like when you have this ladder of energies, you're interested in the lowest, but also in the higher. So if you take the expectation value of a Hamiltonian, you know what the expectation value is, guys? So it's basically the mean average, but in terms of operators. So you would get a number. Okay, so if we took any kind of wave function that could potentially represent your system, and took the expectation value of the Hamiltonian, we would get some kind of number, right? If we took, instead of just any function, the ground state wave function, we would get the lowest number possible, and this would be the ground state energy, right? So this is called the variation principle, but this is just really a simple piece of math. This is not even physics or chemistry. So what we want to do is to search in some set of those trial functions for the wave function that will give us the lowest energy. Now, so this is kind of where the fun starts, because we can take different kind of sets of those wave functions. So the simplest possible wave function that could possibly represent an electron system is a Slater determinant. So this is just the determinant of a matrix where the elements are one electron functions. And we say one electron functions, it's not like we know what those functions are, build them smallest possible set where we can look among the single Slater determinants. If you want a bigger set, so if you take a bigger set, then you get lower energy here, right? Because you search a larger set, so then your minimum can be smaller, and you get better result. So you can take all or some linear combinations of those Slater determinants. So this search among Slater determinants is called the Hartree-Fock method, and this is kind of the most basic quantum chemistry computational method. So you search amongst all Slater determinants, and this gives you some wave function that approximates the real one, and some energy which approximates the real ground state energy. If you take the multi-determinant, so those linear combinations of Slater determinants, then you got yourself a multi-configuration method, and you have some kind of different approximation of both the wave function and the energy. So one of my slides is missing.
Maybe in the meantime, I make one comment. So if you search for a ground state solution of Hamiltonian problem, the true solution always minimizes the energy. So it's quite important that you, if you.
Yeah, well, yes. Then there are the general states, but we don't have to talk about them. Yes, but the real one minimizes. But if you only, so you can, if you had like the first circle, so all possible wave functions, then somewhere here there would be a real wave function that minimizes the energy. I'm so disappointed because I like made beautiful pictures and now you will see them. Okay, so okay, I'll forget it. You'll never see them. So there is a difference, right? Between the exact energy and the energy that you got, your approximation. And this difference we call the correlation energy, right? And so if you have a Hartree-Fock energy, then the part that is missing, the correlation energy, is about 1% of the total energy. So it doesn't seem like a lot, right? And if you have a better approximation, that it's even less than 1%. But it turns out that this 1% is responsible for getting the right spectra of molecules. So basically all the optical properties of the molecules. The shape of the energy surfaces. Also for the barrier heights of reactions. So if you have a reaction, then if you don't get this correlation energy right, which is 1% or less of the total energy, you will probably get wrong whether the reaction can occur or not. Also, the totality of intermolecular interaction is this in this 1% area, and it's even like orders of magnitude smaller. So it's like 0.1% of the total energy, or even smaller. So it's very important that we don't miss this correlation energy. I think, I don't know if it's important for you, but if we put the Hartree-Fock energy, then this difference is called the total correlation. And if we put something like this multi-configurational energy, then this difference is called dynamic correlation. It's not complicated, but it's an ambiguous concept, just dynamic correlation. So like here we are at a point where I can finally start talking about what I really do, because this is what we do in our group, looking for better ways to get this correlation energy. So we are about half time, right? Maybe you have asked much time as you need. No, I just maybe you can take the chocolates if this is a good point. Since you're the host. Okay, so in those multi-reference methods or multi-configuration methods, we have a reference wave function that can be assumed in a form of linear combination of at least two Slater determinants. And we say that if we have a multi-reference wave function, then we get this static correlation. So the static correlation is usually responsible for the description of bond dissociation. So if you have bond breaking, stretching, and so on. But then we have the missing part, the dynamic correlation. And there are like already multiple techniques to get this. The most kind of well-known are perturbation or perturbative corrections. You can add this density functional theory correction. So this is from this, right? It's based on electronic density. And we recently introduced some formulas based on so-called adiabatic connections. We have many projects that utilize this adiabatic connection. And I took the project related to non-covalent interactions, mostly because it has the best pictures, because it's nicer to show. So non-covalent interactions are exactly what they seem like. So non-covalent means the ones where there are no covalent bonds, right? So you can have two water molecules. You can have some kind of dimer, like benzene dimer here. Here you have some chains, or a complex. But also you find them inside molecules, right? So like the molecule here, like this part of the molecule interacts with this part of the molecule, and so on. So non-covalent interactions, we see them usually as the ones responsible for dimerization, supermolecular structure, generally structural stuff. But the truth is that there is more to non-covalent interactions. So, for example, you have something called chemisorption, where you have, for example, a surface, and then you have some molecules interacting with the surface, right? So at first they interact non-covalently, right? But at some point, the interaction can become so strong that those bonds break, right? And part of the molecule reacts through the surface. Then you can have an interaction with a metal cluster. So this doesn't look difficult to, let's say, understand or compute. But metal clusters are notorious for not being able to be described by those simple reference methods. So the ones based on Slater determinants. Then you have materials under strain, so like pressured materials or stretched materials, reactions in vibrationally excited states. So you have bonds that are stretching here, and then you have molecules that undergo a chemical reaction. And then sometimes you have a complex that is created, and then this complex undergoes a chemical reaction. So these are all systems that you have to using both a multi-reference method, so not like hard-to-fork, and you have to have a very good description of the correlation energy. So these are very difficult to describe. And I haven't been speaking a lot about this, but like we do none of this by hand on a piece of paper or even like with the help of, I don't know, Mathematica, or I don't know what's the software, Maple, right? That's something like that.
Mathematica is probably more popular, but
Uh-huh.
I have opinion that from somebody that for partial differential equations, Maple is better in certain aspects.
Right. So instead of like popular, let's say, software packets like this, we have to have codes that are very well written and optimized so they can efficiently calculate certain things that we need. And so we also need good approximations for the wave function. And a very popular approximation that we use is a complete active space wave function. So this is more or less, like I told you, this linear combination of Slater determinants. This can be very expensive or less expensive depending on how you create this. One kind of more exotic wave function is this generalized valence bond perfect pairing. So it's fairly cheap. It describes very well bond breaking. But it has some limitations. And then there are others. There is this density matrix normalization group, which is kind of like complete active space wave function, but with like lots of Slater determinants, but written in a way that it's not so horrible to compute. So one of those cheapest options is this generalized valence bond that is written as an anti-symmetrized product of geminals. And geminals are these linear combinations of orbitals. You know what orbitals are? So these are basically like functions describing a single electron. So in principle, geminals describe a pair of electrons, right? So a pair of electrons, then a pair of electrons is can be just a pair of electrons somewhere, or a pair of electrons that creates a chemical bond, right? So this is basically, this form is why this wave function describes well the stretching and compacting the chemical. And if you write the energy that is that corresponds with this wave function, you have the single electron part, the electron correlation within a geminal, a single geminal, and all the electrostatics and exchange between electrons, right? So you have some correlation, but not all of the correlation. So this is again something, scaling is something that relates to efficiency of the algorithms. So if we say it scales as number of geminals times the number of basis functions, so basically we say if we have I will just write one line. So the cost, if you have, let's say, one electron, right? And it's okay, or maybe the time of calculation. And it takes 10 seconds to calculate. And then if you have 2 electrons, then it will take it would ideally take 20 seconds, right? But actually it will take times 10 for sure. To the 5th power. This is an approximation, but it's more or less. Okay, so we want this to be as low as possible. Just to give you some notion. DFT, for example, has normally the scaling n to the 5th, but it can go down n to the 4th. And so this is probably the cheapest you can go with quantum chemistry. And false PI, which is like the holy grail of quantum chemistry, is n factorial.
Quite so it's almost n to the power n by scaling number, right?
Yeah. So you want this to be, let's say, if you have something better than DFT, you want it to be n to the 5th, n to the 4th would be a dream. That's the. And hydrophone, because we know hydrophone already, it's n to the 5th. Okay, so if this is n to the 5th, this is pretty good, right? But you still have correlation to calculate. Okay. So one way to get back the correlation would be one of those perturbative corrections. They have their advantages and disadvantages. We derive something called extended random phase approximation. I won't show you the derivation because like it uses a lot of math, and I don't think it's super interesting unless you want to develop your own methods. But anyway, we have this correction that introduces this intergeminal correlation. So we correlate between those guys, right? And this is pretty good for modeling chemical reactions. But we underestimate the interaction energies in non-covalent interactions, which is really our goal to get right. And so we can come up with something that is called embeddings. So we put every geminal, or we can divide our system into fragments. Those fragments can be geminals or can be bigger. And we kind of embed it in the field of all other of the other stuff, right? So we kind of have the interaction within this fragment, and then interaction from all the other fragments. And so we have now a single fragment correlation, and we have a 2-fragment correlation. And the nice thing about this is that we get better in intermolecular energies, but we also get better scaling for this of this correction. So it's cheaper. So it's better and it's cheaper. So this is unheard of. So now I will show you some examples. Because I really wanted to like go all the way and show you that we have like, well, I won't show you the code, but the code exists. But also some maths and physics. But also I want to go kind of to some chemical examples. So you see that it really makes a difference if you use a good method, and you can then get some insight into the system. So for example, you have an ethylene diamond. So 2 carbons, 4 hydrogens in each molecule. And then you just do the simple thing, you twist the bond in one ethylene. So the electrons in this bond basically become free radicals. And what does it do to the interaction? So you can see that, well, let's look at this this plot. So we have just generalized valence bond method. So we have no bonding. Here, there is no minimum in the curve. That means there is no interaction between those molecules. Then we add the correlation correction. So we have now, well, it looks deep on the plot, but it's really just very small numbers. This is like 1 calorie per mole. This is not a lot. And then when we tweak the bond, if we just use this GVB method without the correction, nothing changes, right? This is exactly the same as not twist. But when we use the correction, we get the minimum. It's not as deep as the previous one. So this binding energy is about 40% smaller than in the flat dimer. And if we visualize the interaction, we see that the interaction is now kind of more localized right here on this on those bonds. Well, I guess the colors are not really that obvious, but we get most of the interaction here is from this bond, and here we have much less interaction. So this destruction of this CC bond eliminates a lot of the interaction between the molecules. And here we have a similar, well, an example that is actually important because those molecules in nature react with each other. So fluorine is probably the most reactive molecule in the universe. And so it reacts with everything. But in its molecular form, it has a non-covariant interaction with ethylene. And so we have if we just have the this equilibrium geometry, so like it's normally in nature, we have some small interaction, right? But then if we stretch this bond, then we get stronger and stronger interaction. This interaction is different so much, then probably it's facilitating now the chemical reaction. And this is like an fact situation because why would this bond stretch on its own? Well, when you give some energy to the molecule and you hit the right energy levels, it starts vibrating, right? So the bond starts elongating and compressing, right? So basically, if you heat up a molecule, and then it starts vibrating, and the bond starts stretching. So if you heat up this molecule, it starts interacting more strongly with this ethylene, and it can undergo a chemical reaction. Okay, I don't know if this is because it's basically showing the snippet. Sorry. So we found out that the elongation of covalent bonds can lead to enhanced interaction between monomers. So, okay, the van der Waals minimum. So the van der Waals minimum. So, for example, this is the van der Waals minimum. So it's the minimum in non-covalently bound systems. This is produced by an interplay between the growth of the negative contribution of dispersion, which I can tell you about another time, and the positive contribution of exchange interaction to the energy. Exchange interaction is this basically the quantum chemical words, more or less, for Pauli repulsion, right? So you know what it is that, for example, two electrons cannot have the same energetic state. And this growth of dispersion, so this is an attractive interaction, is partly due to growing polarizability of electrons. And this is the polarizability is like sensitivity of electrons to electrical field. And partly by just migrating electronegative. And electrons are forming that form the pi bonds. So, for example, this one here. Play a special role in van der Waals interactions. So this is just some of the things that we came up with when we were mostly just testing our method. But these are things that are quite difficult to describe because it involves describing two kind of challenging effects at the same time: the bond stretching and intermolecular interaction. Okay, and I think I will stop here because the other thing are just some curiosities. If we had too much time, we could talk about them, but we don't. We are basically as planned, I think. So, do you have questions right now, or you know everything now?
So maybe we welcome questions from your side. You can ask some open questions of any type.
So I'm interested about actually the work that you perform. Do you specialize in finding like better methods like this GVP, for example, right? So Are you trying to maybe improve those methods, or rather kind of see some interactions by using?
So basically, we are looking at this correlation energy, right? So this small amount of energy that is kind of difficult to describe. So there are very expensive methods that are kind of good, right? And then there are cheap methods that are not very accurate. But it's when I say expensive, right? Then it's not about money. It's about that there is no supercomputer big enough to calculate, for example, a DNA molecule, right? With those approximations. So we come up with like better approximation for this correlation energy. So first we write it down and like we try to get the formula right. Then we write it into the code, and then we test it, right? And if it's a good approximation, then we try it on more and more challenging systems, and sometimes we also like solve like chemical problems. Like I have collaboration with experimentalists, and so they want me to explain why this photoswitch molecule is doing the things it does. So I do the calculations, and then I just use some methods already.
Also about this formula, like into the part of pi, I see there was some like interactions or something to the power of 4, right?
Yeah, because so I this one. Yes, so so the scaling is kind of like the bigger the system, the more expensive the calculation, right? But it's not, when I say, well, if there is 2 electrons, it's more expensive. This is a bit of an approximation as well. So the Geminos are those functions here. So the number of Geminos you can tune it, but it's more or less the number of electrons divided by 2. Okay? And the number of basis functions, so to have a Geminal, you need orbitals. But to have an orbital, so the orbitals are also optimized. And they are optimized as linear combinations of some functions from some set called the basis set. And depending on how big this set is, that's the number, right? So this is how big the basis set is. So basically that's
Any more questions? How many interacting particles you can consider? I know there are levels of approximation of that, but in your system, what's your life record? What's your life achievement in terms of number of interacting particles?
Which method I used? So right now I'm using basically DFT to calculate this dynamics of a photoswitch. So the photoswitch is 39 atoms, right? So that's kind of the medium for DFT. For this kind of methods, I think also we go into hundreds of electrons right now. But we are, because the cost of the method is not just what you see here, but it's also how well it is encoded, right? How well the code is. So we also use tricks to get the code. So this is changing.
So from physics perspective, at least I heard that fundamental description of any interacting particles can be achieved up to 10 interacting particles. Otherwise, the Hilbert space becomes too big.
Okay, yeah, but we only look, so in the our approximations, they are basically 2 electron interactions, right? We don't need more. Yes, you're right that if we call interacting particles, just how many bodies are basically 2 bodies, 2 body problems.
So how about, I know this is maybe nightmare for physicists to model dynamics of chemical reaction fundamentally, right? Initially, you essentially observe initial state and final state. But to observe the dynamics, I heard that at very low temperatures, people conduct some chemical reactions, and they're able to model things quite fundamentally as with respect to all existing physical processes. Can you make any comment on that?
So chemical reactions are quite tricky because in certain points, this Born-Oppenheimer approximation stops working. So you can say, well, I'll pretend it's working. Sometimes like you can do a simulation that it's still okay. But basically what people do, and this is quite clever, is that they're calculating. So in certain points, the system is allowed to be outside of this Born-Oppenheimer. So we lose this Born-Oppenheimer just for like particular points of the reaction. And this is kind of approximating how the reaction is really going. So you're calculating a certain index based on the wave functions, and then you decide that this is the point where Born-Oppenheimer doesn't work. But then it's you go back to this Born-Oppenheimer, because if you didn't, then you would be just basically dead. You would calculate for it.
How about relativistic effects? I know that in uranium atom, you observed on the last shells a kind of relativistic electrons, but most elements doesn't need it. Can you make a comment on that?
So I think I usually don't deal with very heavy atoms, but from colleagues that do and did tests, I know that already sulfur is tricky. So as low as sulfur, you should consider relativistic effects, and then there are corrections. Basically, if it's not very strong, there are some corrections that are fairly efficient. You can include them, and it's all like all the other stuff is the same, right? You just include a relativistic correction.
Maybe another question from the quantum computation point of view. You know, there's IBM Quantum Experience, and people try to model new chemical compounds. And usually compounds with no so sophisticated structures could be somehow captured by a quantum computer. Do you have any type of suggestion for us which systems we can consider for a quantum computation perspective, and which system we should abandon?
I don't really know. I know that from some people that are trying to do this algorithms for quantum computing, that basically the interesting systems are the ones with strong correlations. So, for example, like metal clusters, but also some not. So, if you see like that there is a lot of strong correlation in a molecule, then this might be interesting for you. But I don't have any experience with this.
I see. Because there are some companies producing, like Bayer. They have created units of developing quantum chemistry from the point of view of using quantum chips.
Mm-hmm.
So that's why I'm just I just came across personally such a person working. And then there's a question: if you want to advertise Qiskit programming language, Qiskit environment created by IBM Quantum Experience, if you want to address this problem to chemists and people associated with chemical problems, which systems we should aim and which system we, as physicists, shall we pre-analyze?
Right. So I think I think there are already some papers on this, right?
Yeah.
You can look, but basically this. I know that one group that is working on this DMRG is, let's say, France. So density matrix normalization group, and they say they can really benefit from quantum computing, and because I'm trying to remember why this was. I think they like heavy parallelization, so I don't know if this is something that you can do. But we actually have a diploma student who developed some quantum chemistry methods for quantum computers. I can give you the contact. Maybe he's more competent than me in this.
Maybe very last question: if some physicist or computer scientist wants to become a quantum chemist, what's the first software he's supposed to touch?
So I would say that you should first, that depends on what you want to do. Do you want to compute or do you want to develop? So that's, if you want to develop, then basically try learning any programming language. Well, not Java, but Fortran, maybe C, or but Python is also more and more popular in this community. And software, the easiest I think is to get into is Psi4, because it's based on Python. It has great tutorials. You can program a little bit in this, and it's easily interfaced with other software.
Any more questions? How about machine learning? To what extent it can be successful or unsuccessful?
So people are really getting into machine learning over the last, I say, 5 years in quantum chemistry. And there are I think 2 areas where it seems to be useful. One is drug and material design. So you want to design molecules that have certain properties, right? So you want to compute many molecules and you want to see their structures. So you don't want to calculate one by one. So you can use machine learning to just learn what kind of molecules or structure we are looking for. And the other thing is density functional theory. where you constantly look for the approximation for this. I already erased it, so doesn't matter. Basically, you're looking for approximation for this energy, for this form of this energy function. So people use machine learning to kind of fit some parts of the function to known data.
I see, I see. Because I'm asking because, you know, the paradox is that there's more and more people with computer science diploma, and some even work at university, and some of them even doesn't have idea what to do. And there's a certain potential of people that you can customize for your purposes, scientific purposes. So those questions from certain perspective are of practical nature in that sense, right? So that's why I'm just asking.
So when it comes to, let's say, human capital, right? That's what you're asking. I would say that quantum chemistry is constantly looking for people with computer skills and computer programming skills and knowledge about algorithms, because most people that go into quantum chemistry are either physicists or chemists. So this kind of computer illiteracy, okay, this kind of sounds offensive, but the fact that a lot of us don't have formal training in computer skills, it's becoming a problem, because we need better algorithms, and better efficiency, and less messy codes.
Yeah, I guess you have quite many students of very young age, first or second year of first of engineering degree. So you have potential, to shape them somehow. And quite recently, I came across the company that's named Drug Discovery. Have you heard about this type of software? They start to sell the software to some Polish institutions related with quantum chemistry. Are you aware of any of their products?
Well, I don't know the company, but drug discovery is one of the main goals for quantum chemistry. So I'm not surprised. Basically, the better computational methods we have, the more we can scan big sets of molecules for the required properties. And it's not just drugs; it's optical materials and stuff.
What is the best salary you could have in quantum chemistry? I'm just asking because in quantum technologies, I heard about $1 million per year if you're under very good institutions and projects.
I don't know, but I know that the companies that are developed the COVID vaccines hired hundreds of computational chemists. They have good salaries, but it's not CEO salary. It's just a good salary for a scientist.
All right. Any more questions? If not, let us finish your game.
I guess never mind.
I believe.
Also me. Don't count me.